This is the brief on complex vector identities and scalar field dynamics. So this is all about a deep dive into vector identity problems. And what's really cool is how visualizing differential operators, just by using the simple properties of the position vector, can reveal some pretty crucial geometric consequences. We found 3 essential insights that come from breaking down these complex identities. Okay, first up, decomposition. Looking at the divergence product rule, we see that the total outflow is really an additive superposition. It's made up of 2 parts: the position vector's own intrinsic divergence, which is scaled by the scalar field, plus this additional effect that's driven by the field's gradient. Second, we've got vanishing terms and transport phenomena. You get this fantastic visual proof showing that the cross-product divergence is identically 0. I mean, both component terms just vanish. Plus, another identity, one that's fundamental for modeling transport, decomposes into the squared gradient magnitude and a product with the Laplacian, which is absolutely essential for modeling diffusion. And finally, there's the BAC-CAB rule. It's used to fully define these really complex curl identities, and it demonstrates how several different vector fields have to combine just so to accurately define the resulting intricate rotation. By decomposing these identities, we uncover the fundamental geometric rules, essential vanishing conditions, and the entire mathematical framework behind physical transport models.